Okay, so we have a hydrocarbon fuel that is characterized by a mass percentage of C in carbon and H in hydrogen. This means that if we have 1 kilogram of a fuel, in this 1 kilogram of fuel, we will have C kilogram of carbon and we'll have H kilogram of H. This is why we say that these represent percentages in mass, because each 100 kilogram will contain 100 times C kilogram of carbon and 100 times H kilogram of hydrogen. Now, they want us to go through different steps. First, we want to find the quantity of air just required for complete combustion. And we want to determine this quantity first in number of kilomole of air required for complete combustion of 1 kilogram of fuel. And then we will deduce the mass of air required per kilogram of fuel. So let us go first over this question together. So let me open a whiteboard. The approach is really simple. All we have to do is to determine what is the quantity of oxygen that we need. Okay, so we start to say, if we have C kilogram of carbon, how can we find the number of kilomole of carbon that we have? If you have a mass and you need to determine the number of kilomole, what do you do in general? You should divide by the molar mass of carbon. We know that the molar mass of carbon is 12 kilogram per kilomole. Okay, so in order to find what is the number of kilomole present in this 1 kilogram of fuel, all we have to do is to say that the number of kilomole is C over 12. Okay, so knowing the percentage in mass, we can say that in 1 kilogram of fuel, we will have C over 12 kilomole of carbon. Now, if we consider for hydrogen we have that we have H kilogram of hydrogen. So now we can say that if we want to consider the number of kilomole, let's say, of H2, okay? So if we consider the number of kilomole of H2, it will be H over 2 kilomole. Okay, or you have the freedom or to consider H2 or to consider H, and now we'll discuss this together. So if you put H2, then you have H over 2 kilomole, and if you just say number of kilomole of H, it will be H kilomole. Okay, and it depends on the reactions that you write. When you have a combustion, what are the main two reactions that take place? We know that carbon will do reaction with oxygen O2 in order to form the molecule CO2. So we can say here, since in 1 kilogram of fuel, we have C over 12 kilomole of carbon, then from this reaction, from this chemical reaction, if we have C over 12 kilomole of C, we will need also C over 12 kilomole of O2 in order to produce C over 12 kilomole of CO2. So this is, and if we talk in kilomole, so the number of kilomole needed for C is equal to the number of kilomole needed for O2 equals to the number of kilomole of CO2 produced. And now, if we consider for H2, the equation for H2 is the following. We can write that H2, so we know that when H2 and O2 will do reaction together, they will form H2O. But of course, we should pay attention for coefficients. So we need to have the number of atoms of H in both sides equal, the same for oxygen. So from here we can say the following. If we look at the following formula, or we put as coefficients here 2H2 and here 2H2O to get, because in this way, if we consider the number of atoms H from both sides, it will be 2 times 2 and 2 times 2, 4. And for O2, here we have 2 and here we have 2. So this is the proportion that we should have. You can have several forms. You can write H2 plus half O2 equals H2O. It's also right. So any combination will be the same, provided that we have proportional coefficients. Now, once I write this, okay, in order to determine the number of kilomole, do you see the screen? You
Yes,
see
we can.
board? Okay. So now what can we deduce? We can say that I will just expand it. Okay. You can say that since I have H over 2 kilomole of H2, okay? And from this relation, I can deduce that the number of kilomole of O2 is the number of kilomole of H2 over 2. So if I have here H over 2 kilomole of H2, I will need H over 4 kilomole of O2 in order to produce H over 2 kilomole of H2O. Okay, and then now I can say that in total, from these two equations, in total, the number of kilomole of O2 required for stoichiometric reaction, so complete reaction and no O2 will remain in my problem, is to have the number of kilomole of O2 should be equal to C over 12 plus H over 4. Okay. Now, we know that they asked not for the number of kilomole of oxygen, O2, they asked for L0, which is the number of kilomole of air that is required to have the stoichiometric combustion. And the information here that we need is just what is the volumetric percentage of O2 in air. We know that the percentage of volume of O2 in air is 21%. So the percentage is just 0.21. Okay. So we can just say now that the quantity of air required, so L0 is just 1 over 0.21 times C over 12 plus H over 4. So this is the number of kilomole of air required for the combustion of 1 kilogram of fuel. Okay, so it's enough for me to give you what is the percentage in mass of carbon and what is the percentage of mass of hydrogen in the fuel. Then you can deduce what is the number of kilomole of air required for 1 kilogram of combustion. And if you want to discuss the unit of L0, the unit of L0 will be kilomole of air per kilogram of a fuel. Now, why it's very important to know this number? Because actually, you know that in cars, will not always have stoichiometric combustion. We can have incomplete combustion. This is when we give a quantity of air that is smaller than required. And of course, we should pay attention for this, because if we supply, if the quantity of air is very small, very smaller than L0, then we'll have production of CO. And we know that CO2 is harmful, but CO is also more harmful than CO2. And we know that one of the most, if you want, important criteria in cars emission is to reduce the amount of CO. And that's why we should be able to control this amount by providing a sufficient quantity of air. And the majority of cars, if you want, will work in fractions of L0. We say that alpha can be smaller than 1. Alpha is the proportion of air given to the required. Okay, so let's say here we found that L0 is 1 over 0.21 C over 12 plus H over 4. If I provide a quantity L, so if L is smaller than L0, I will have a incomplete combustion. And we define here what we call the coefficient of excess of air, alpha. Alpha is equal to the real quantity delivered over the required quantity for complete combustion. So in case alpha is smaller than 1, this means that the combustion is incomplete, and we will not have only formation of CO2, but also will have formation of CO. And we say that we should control alpha in cars. We should not have alpha very small. And we can allow, let's say, for values up to, let's say, down to 0.8, but not lower. For very lower values of alpha, the toxicity of the emission gases will be really high. Now, in this, they also asked us to determine the quantity of air in kilogram. And it's very simple to do it now, because once we get the quantity in kilomole, we know that by definition, the number of kilomole is equal to the mass over the molar mass. Okay, so now if we consider that the number of kilomole of air is big L0 per kilogram of fuel, and we know to determine now what is the mass required. So what is the number of kilogram of air that is required for combustion of 1 kilogram of fuel? This is what we call small L0. Okay, so this is what they are asking for. This is small L0. We should divide by the molar mass of air. So now we say then we deduce that L0, which is the number of kilogram of air required for combustion of 1 kilogram of fuel, it's equal to the molar mass of air, which is nearly 29, times big L0. Okay, so this is how we can relate small L0 and big L0. This was the first step when we considered a complete combustion. Now, in the second question, they said we have incomplete combustion. Okay, and whenever we have incomplete combustion, things will be more complex, because we'll have to consider new products. You know that when you have incomplete combustion, in addition to the conventional products that are CO2 and H2O, we will have also the formation of CO and H2. And then we have to write more than one reaction, because we'll have now different possible reactions that can take place. Because we now, in addition to the first formulas of combustion that we already know, we can say that C, so we have C plus half O2 will form CO, and hydrogen atoms will combine together, so H plus H, to form H2. Okay. Now, to be able to determine the quantity of products, we need always to go back to the principle of conservation of mass. Okay, so here, what are the elements that we have? We have carbon, we have hydrogen, and we have also oxygen and air. Okay, so since we have three elements, by conservation of mass, we can say that the mass of carbon in a product is equal to the mass of carbon in reactives. And also we can say, we can do analysis in number of kilomole. And we can say that the number of kilomole of C before combustion, okay, is equal to the number of kilomole of C after combustion. Now, we already know together from the analysis that we did together that before doing the combustion, the number of kilomole of C was C over 12, because we have C kilogram of carbon. Then the number of kilomole just before combustion is C over 12. Now, we know that also that C, part of carbon will do reaction with O2 to form CO, and part of carbon will do reaction to form CO2. So since the quantity of carbon was divided into two reactions, then we can deduce that the number of carbon before will be equal to the number of kilomole of CO, because you know that if we have 1 kilomole of carbon, it will lead to the formation of 1 kilomole of CO. So the number of kilomole of CO will indicate what is the number of kilomole of carbon that reacted with oxygen to give CO. While if we consider now the other quantity, we have a quantity of C that combined with O2 will give us CO2. Also here, we can say that 1 kilomole of C will lead to the formation of 1 kilomole of CO2. So the total number of kilomole of C is the summation of the number of kilomole doing this reaction plus the number of kilomole of C doing the second reaction. And since this number here is equal to the number of kilomole of CO, and the number doing the second reaction is equal to the number of kilomole of CO2, so we can say that C over 12 is number of kilomole of CO plus number of kilomole of CO2. So from the first element analysis, we were able to find equation number 1. Okay? Now, if we consider now for H, we'll do exactly the same procedure. So the number of kilomole of H before combustion, and we know that the number of kilomole of H before combustion was just equal to H. Here you have the freedom, okay, you have two approach. You can say, I want to do my reasoning for H2, yani the number of kilomole of H2 before equal to the number of kilomole of H2 after. It's exactly the same. Yani if we write the two equations, we'll do both for you. If we write the two equations, you have just proportionality between the equations. Because if you choose to say NH2 before is equal to NH2 after, your equation will be the following one. You say, before combustion, okay, I have H, we know that we have H kilogram of H, which is equivalent to H over 2 kilomole of H2, as we discussed before. So we can write then that H over 2 is equal to. Now, if we do the analysis for H2, okay, H2 will form H2O, يعني will do a first reaction to form H2O, and another reaction to just form H2. So we can say that H over 2 is equal to the number of kilomole of H2O plus number of kilomole of H2, because we have some H2 molecules, if you want, will do reaction with oxygen to give H2O, while other atoms H will combine, each two atoms will combine with each other to form an H2. Okay, and if we want to write it instead of doing an H2 before equal an H2 after, if you want to write an H before, so if you want to write an H before equal an H after, then what will happen is just that we will multiply by 2 all terms of the equation, because in the initial state, if we talk about atoms H, since we have H kilogram of hydrogen, this is equivalent to H kilomole of hydrogen. So the number of kilomole of hydrogen before is equal to H. Now, in the products, we have H2O and H2, okay? And we know that each molecule of H2O contains 2 kilomole of H2, okay? So then we can, 2 kilomole of H, sorry. So we can say H is equal to 2 times number of kilomole of H2O plus each molecule of H2 contains 2 kilomole of H. So it's a plus 2 times NH2. So if you divide now by 2 the equation, you will go back exactly to the same result before, which is H over 2 equals to NH2O plus NH2 is the result of the balance of hydrogen, okay? And we still have one equation that we didn't use, which is the conservation of mass of O2. So now we can say that the final relation that we can write is that number of kilomole of A2 in reactives is equal to the number of kilomole of O2 in products, so before combustion and after combustion. Now, before combustion, the number of kilomole of O2, how can we determine it? Look, here they told us we have incomplete combustion. So they told us that the real quantity of air, how you can calculate the real quantity of air? It is alpha, which will be given for you. So whenever I say incomplete combustion, I will give you a value of alpha smaller than 1. So the quantity of air provided is alpha times L0, where L0 is the required quantity of air for stoichiometric combustion. And we have already found together that for stoichiometric combustion, L0 is C over 12 plus H over 4. Okay, so now we can say since oxygen constitute 20% in volume of air, so NO2 before is just equal Dear students, do you hear me now?
Yes.
Okay, please can you just tell me when we had the cut شو كنا عم نقول? So we were talking about the number of kilomole
Alpha
of
equals C over 12 plus H over 2.
okay. طيب, great. So we were talking about the conservation of number of kilomole of O2 before and after combustion.
Yes.
So NO2 before equals NO2 after. And we said that because they told us that we have incomplete combustion, then we can deduce that the quantity of air delivered is smaller than the stoichiometric quantity. So it's equal to the coefficient alpha, which will be smaller than 1 because we have a deficiency in quantity of oxygen, times L0. Okay, and since we already calculated L0 before, we just replace L0 by C over 12 plus H over 4. Now, since we need the quantity of oxygen, and this is the quantity of air, we just have to multiply by the volumetric percentage of oxygen in air. And we know that the quantity is 21%. So NO2 before is 0.21 L, which is equal to 0.21 times alpha L0 equals to 0.21 alpha times C over 12 plus H over 4. And this quantity should be equal to NO2 after. And as we discussed together, the quantity of O2 after will be divided now into 3 parts. Why? Because in the products, okay, we said what are the products? CO, CO2, H2O, and H2. So oxygen will be divided into 3 parts. One to do reaction to give CO, another part to give CO2, and a third part to give H2O. And we can say, since the mass of oxygen is the same before and after, so since we are determining the number of kilomole of O2, it will be the summation of number of kilomole of O2 present in CO plus number of kilomole of O2 present in CO2 plus number of kilomole of O2 present in H2O. So we can say, since O2 contains 2 oxygen atoms, while O contains just 1 atom oxygen, so we can say that NO2 is NCO over 2 because we need each 2 molecules of CO will give 1 molecule of O2 plus for CO2 we have here O2 and here we have O2, so it should just NCO2 plus, now for H2O it's like CO, we have each 2 molecules of H2O will give us 2 atoms of oxygen, so we should also here do NH2O over 2. Okay, now we already have 2 relations developed before. Okay, and here we have 3 terms. So to be able to close our system of unknowns, we need an additional information. Yani we are not able to determine what is the quantity of products unless we have additional information that is given. This is why in this problem, they told you that experimentally, okay, we can determine experimentally the factor X, where X represent, as they said, the number of kilomole of H2 over the number of kilomole of CO2. Now this parameter, they can give you any of the parameters. Okay, they can give you the ratio of H2 over, let's say, H2O or NH2 over NCO, etc. Because you just need one extra equation to close your system. Because now, if I know what is NH2 function of NCO2, I can try to express, if you want, all my parameters also function of CO2. How can I do this? So I can start to say that according to this relation, I can replace in my equation. I know that NH2 can be replaced by X times NCO2. And since from my previous analysis, I determined that we have a relation between NH2O and NH2, okay? Because if we go back to the previous relation, we can say that what is by definition NH2O? It's equal to N of, it's equal to H over 2 minus, so it's equal to H over 2 minus NH2. So now if I replace NH2 by its value, which is X times NCO2, okay, I can have just, instead of H2O, I can express function of CO2. And I will do the same for NCO, because NCO can be also related to NCO2, since also from my previous equation, I got that NCO can be replaced by C over 12 minus NCO2. So when I did this, if you want, I was able to reduce my equation to only one unknown, which is N of CO2. So after replacement, I will replace together. After replacement, I just have to find NCO2 function, of course, of the other parameters. And once I have NCO2 function of the other parameters, I can, if I give you the numerical values of the parameters, you can calculate them. And once you get one NCO2, you can replace in the other equations to get all remaining products. So you can get NH2, you can get NCO, etc. Okay, so let me do the replacement. So I will just put it again in a clearer way. So as we said, the number of kilomole of O2 before is 0.21 times alpha L0 equals to, now we said the first term is NCO2, we'll keep it as it is because we will express all other terms function of NCO2. So now, instead of NCO, as we discussed, instead of NCO, we'll replace it by C over 12. So C over 12, since it is NCO over 2, C over 12 will become C over 24 minus N of CO2, okay? So over 2 again, so minus NCO2 over 2, because we need to have NCO over 2. And NCO is C over 12 minus NCO2. So it's equal to C over 24 minus NCO2 over 2. So this is the replacement of NCO divided by 2. And finally, I will do the same for NH2O, okay? We said that we should do NH2O over 2. And NH2O can be written as H over 2. So it's H over 2 minus NH2. This is why when I divide by 2, I will get H over 4 minus NH2 over 2. And as we said in the problem, they gave us an H2 function of the quantity of CO2. They said that they gave us X, so we say that NH2 is simply X times CO2 and CO2. So now I will replace here NH2 by X times CO2. So here X times NCO2. And now all I have to do is to group all terms that are factor of NCO2. So I get 0.21 alpha L0. I will take C over 24 and H over 4 to the other side because I know them. They are given. So minus C over 24 minus H over 4 okay, equals to, now I will take NCO2 in factor. So if I take NCO2 in factor, I have 1 minus 1 over 2 and minus X over 2. Okay, so this will be equal to 1 minus X over 2. Okay, and now I conclude that NCO2, so NCO2 is just 2 over 1 minus X, so it's equal to 2 over 1 minus X times this term. So if I call this term A, okay, I will call this term big A. So NCO2 is 2 over 1 minus X times